All right, let's get right into it. Today, we're basically becoming scientific detectives. We're going to break down a really cool technique in virology called the antiviral entry assay. We're going to find out exactly how scientists can prove if something can stop a virus dead in its tracks.
So here's the big question, right? It's one thing to find a new compound, maybe from a plant or something, and think it's an antiviral. But how do you actually prove it? Specifically, how do you show that it works by stopping the virus from ever getting inside a cell in the first place? Well, that's exactly what this assay is designed to figure out.
I want you to think of this whole process as a detective mission. Picture this. The virus is the bad guy, trying to break into a high-security building, which is our cell. And this new extract we're testing, that's our brand new top-of-the-line security system. Our job is to run a controlled test to see if this system can actually keep the bad guys out.
And this right here, this is our investigative toolkit. This diagram shows the entire 7-step game plan we're going to follow. It's our roadmap for the whole experiment, from setting the scene all the way to analyzing the final evidence. So let's jump in and go through it, step by step.
Okay, first things first. Just like in any good investigation, preparation is key. Before we can even test our antiviral, we have to carefully set the stage and create the perfect conditions for the virus to try and get in.
So, for step 1, we take our cells and lay them out in a dish. Then, we chill them way down to 4 degrees Celsius. Once they're cold, we introduce the virus. Now, at this chilly temperature, the virus can float around and latch onto the surface of the cells. This process is called adsorption. It's basically stuck to the outside, like a cat burglar, clinging to the side of the building, waiting for a window to open.
But why that specific temperature? Why so cold? Well, chilling the cells to 4 degrees is like hitting a giant pause button. It freezes all the action. It lets the virus find and attach to the cells, but it's too cold for the cell to do anything, including letting the virus inside. It's a really clever trick to get all the viruses lined up at the starting line all at the same time.
Now, before we go any further, let's define the single most important piece of evidence we're looking for. It's called a plaque. Imagine our layer of cells is like a perfectly green, healthy lawn. When one virus gets into a cell, it takes over, makes tons of copies of itself, and then bursts out, infecting all the cells right next to it. This chain reaction kills a whole patch of cells, leaving a clear, dead spot in our lawn. That's a plaque. Counting these plaques is how we're going to count the successful break-ins.
All right, the scene is set. The virus is latched onto the outside of the cells, just waiting. Now it's time for the exciting part. Let's bring in our secret weapon, that antiviral extract, and see what it's made of.
First, we do a really quick wash to rinse away any viruses that are just floating around and didn't manage to grab onto a cell. Then comes the most critical step of the whole experiment. We add our extract. And this is the important part. We warm everything up to 37 degrees Celsius, which is normal body temperature.
So, why the sudden change in temperature? Well, warming it up to 37 degrees is like yelling, "Go!" It flips the switch on the cell's machinery and gives the virus the green light to try and force its way inside. This is it. This is the moment of truth, where the virus is actively trying to break in, and our extract is hopefully standing guard, blocking the door.
So the test is officially running. But a good detective knows that you can't just look at the obvious stuff. You have to clean up the crime scene, get rid of any misleading clues, so you can be 100% sure about your final conclusion.
To do that, we add a special solution called acidic glycine. You can think of this stuff as a disinfectant for the outside of the cells. It completely neutralizes any viruses that are still just stuck to the surface but failed to get in. We don't want them confusing our results later. After that, we do one last wash to make sure everything is squeaky clean.
And this step is so important. We have to be absolutely sure that the plaques we count at the end came only from viruses that successfully got inside the cell during our experiment. This step basically removes all the loiterers and the wannabes, so we're only counting the real successful break-ins. It's all about accuracy.
Okay, we've run the experiment, we've cleaned up the evidence, now all that's left is to see what happened and deliver the final verdict. Did our security system actually work?
So, we take our plates and let them sit and incubate for a couple of days. During this time, any virus that actually made it inside will replicate and form those clear plaques we talked about. After a few days, we add a special stain that colors all the living cells, which makes the plaques, the dead spots, show up as these clear, easy-to-see circles. Then, we just count them.
And this is exactly what we're hoping to see.
Check it out. On the left, with no extract at all, you get a ton of plaques, lots of successful break-ins. In the middle, with a low dose of our extract, you see fewer plaques. That's pretty good. But on the right, with a high concentration of our extract, you see very few plaques, maybe even none. That's a huge win.
And that's the bottom line. It's really that simple. The number of plaques we count is directly tied to how many viruses got in. So, if we see that adding more extract leads to fewer and fewer plaques, we have really strong evidence that our compound is doing its job and blocking the virus right at the front door. You know, at the end of the day, our whole detective story comes down to this one single goal. Every one of those 7 steps, from chilling the cells to warming them up to staining the plate, it was all designed to give us an honest, accurate count of those plaques. That's how we get our answer.
So our investigation was a success. We figured out how to see if we can block the front door. But you know, a virus's life isn't just about getting in. It also has to copy itself, build new virus particles, and then break out to infect other cells. So that leaves us with a really interesting question to think about for the future. Now that we've secured the entrance, what other part of the virus's life cycle could we try to mess up next?